Hello students. So far we have completed the Rutherford's model of atom, and in that model we have seen that this model of atom as proposed by the Ernest Rutherford on the basis of alpha scattering experiment, it could not explain the stability of the atom, and as we have seen, and it could not at the same time could not explain the line emission spectra, yani atomic spectra. Keeping these limitations in view, Niels Bohr, a Danish physicist, in 1930, he made a bold statement. What was that? He says that the classical laws cannot be applied directly to the processes at the atomic level. Keeping these things in view, he combined the classical as well as the early quantum concepts which was given by the Max Planck and the Einstein's photon theory. He combined it. He says that he combines the classical and the early quantum concepts and proposes a new atomic model, which is known as the Bohr's model of the hydrogen atom, which we are going to study in this lecture. That is Bohr's atomic model of the hydrogen atom. And he gave his atomic model in the form of three postulates, which are known as the Bohr's postulates of the hydrogen atom, this atomic model. Now, what are those three postulates? Now, this is the postulate first. What was that? That an electron in an atom could revolve in certain stable circular orbits around the nucleus under the influence of the electrostatic force of attraction between nucleus and electron without the emission of radiant energy. Now, this is the classical statement here in this postulate. He means to say that means we can apply the classical laws. Here we can apply, because he says that electron could revolve in a certain stable circular orbit around the nucleus under the influence of the electrostatic force of attraction. And when a particle is revolving around any bigger object, as per the classical theory, we know that it needs a centripetal force. And that is why he mentioned that this force is provided by the electrostatic force of attraction between the nucleus and the electron. But he further added that without the emission of the radiant energy. Since when an electron revolves around the nucleus, revolution of any, we know that electron is a charged particle, and as per the classical theory, which we have seen in the previous lecture in the Rutherford model of atom, that was the drawbacks of the Rutherford model of atom. What was that? Since the electrons are revolving around the nucleus in circular orbits in the same way as the planets are revolving around the nucleus. But there was as per the electromagnetic theory, classical electromagnetic theory, when a charged particle is accelerating, it radiates energy, it emits energy. When it emits energy, means it loses energy. It will move in a orbits whose size will decrease, and finally it fall into the nucleus. It will follow a spiral path around the nucleus. This was the drawback of the Rutherford's model. But here the Bohr, he says that although the electron is revolving around the nucleus, being a charged particle, but here we can't apply at atomic level, we can't apply the classical electromagnetic theory here. He says that without the emission of radiant energy, okay, it will revolve around the nucleus in circular orbits. That means an electron is in accelerated state. It has an acceleration. As per classical theory, it should emit radiation. But Bohr added that we can't apply the all classical theory to the processes at atomic level. That is why he added that without the emission of radiant energy. And he called these stable circular orbits, in which the electron can exist, in which the electron can revolve. He called these as stationary states. Stationary status doesn't mean that the electron is at rest in these orbits. Rather, it means that electron is revolving in these orbitals without emitting any radiant energy. This is what he means to say stationary status. Thus, from this postulate, we can conclude that there are certain definite stable status having the fixed energy. Why? Why fixed energy? Because the electron is not emitting any radiation. Unlike as was in the Rutherford's model. Because in Rutherford's model, the electron was accelerated, it emits, as per the classical theory, it will emit energy. But he posed a restriction that we can't apply the classical electromagnetic theory at the atomic level, the processes at the atomic level, and it is not without the emission of radiant energy. Electron is revolving around the nucleus, it is accelerated, but it will not in a particular orbitals. These are the fixed orbitals, stable orbitals, in which it is not emitting energy. Thus, we can say when it is not emitting energy, that means we can say there are stable status. There are certain stable status in the atom in which the electron can exist. And these stable status have definite energy. They have fixed energy. This is what we can say from this postulate. Now, postulate 2. Now, the postulate 2, it will give the size of these status. This having the definite energy around in an atom in which the electron can exist. What is that? As per the classical theory, there are large number of circular orbitals can exist in which the electrons can revolve. But there is a restriction in the Bohr's model posed a restriction in the form of second postulate. And this second postulate gives actually gives the size of these orbitals in which the electron can revolve around the nucleus. What is that? The allowed orbitals in which the electron can move, the allowed orbitals are those for which the electron's orbital angular momentum, which is denoted by L, about the nucleus is quantized and equal to an integral multiple of h by 2 pi, where h is Planck's constant, which is equal to 6.6 into 10 raised to the power minus 34 joule second. That is, mathematically we can say that means only those orbitals are allowed. Only those orbitals are allowed for which the angular momentum of an electron, when it is, because from the postulate number first, the electron is revolving around the nucleus in certain orbitals having fixed energy, but there is a restriction in which orbitals it can revolve. There is a condition. It can't revolve in any of the circular orbitals. But there is a restriction. What is that? It can revolve only in those orbitals for which the angular momentum of an electron. Because we know that angular momentum, it is the quantity which is related to the objects which have some angular component related to an axis or related to a fixed point. But here the fixed point is the nucleus. He says that only those orbitals are allowed in which the angular momentum of this electron is integral multiple. That must be an integral multiple of, that is an integral multiple of h by 2 pi, where h is Planck's constant. So we can say that means the angular momentum. In these states in which the electron can revolve around the nucleus, the angular momentum of the electron is quantized. That is fixed. What is this? That's the integral multiple, and that is the integral multiple of h by 2 pi, where n times, where n can have a value from 1. It starts from 1, not from 0. It starts from 1. N is equal to, n can be 1, or it can be 2, or it can be 3, and so on. And this is called as the principal quantum number of the orbit. Principal quantum number of the orbit. So thus from this postulate, this shows that there are only only those orbitals are allowed in which the angular momentum of an electron around the nucleus, about the nucleus, is integral multiple of h by 2. Integral means it can be either h by 2 pi, or 2 times the h by 2 pi, or 3 times the h by 2 pi, or 4 times the h by 2 pi. Integral, it can't be 1 point h by 2 pi. That is not integral multiple of h by 2 pi. It should be either 1 times h by 2 pi, or 2 times h by 2 pi, or 3 times h by 2 pi, or 4 times h by 2 pi, and so on and so on. These are the allows, these are the orbitals which are allowed for the electron in which it can revolve around the nucleus. This is the condition number 2. This is the postulate 2 as proposed by the Bohr. And third is the third postulate that was incorporated by the Bohr. This is the postulate in which he incorporated the quantum condition. Quantum that had been given by the Max Planck and the Einstein's concept of photon. He introduced that concept in the postulate number 3. What is that? The atom emits radiation. Because in the Rutherford model, as I told you, that it could not explain the line emission spectra of atoms, because atoms, each and every element has its own line emission spectra. As per the Rutherford model, when we have seen when the electrons are revolving around the nucleus, we came to know that the spectra, as per the Rutherford model, that must be the atomic spectra, that must be continuous. But experimentally, it was observed that the spectra are line spectra. That was the limitation of the Rutherford model. Now, as per the Bohr, he says that the atoms emits radiation when electron makes a transition. When electron makes a transition from a more energetic stationary state, from a more energy initial stationary state to a lower energy stationary state. When the atom will emit an energy, it will emit a radiation when an atom makes a transition from a more energetic initial stationary state to a lower energy stationary state. So thus, this is in this third postulate, actually, Bohr explains that how line emission spectra, actually this is the explanation to the line emission spectra. Now we will discuss that later on, how the Bohr's model, how it explains the line emission spectra of the atoms. And when it makes a transition when an electron in an atom makes a transition from one stationary state, from some initial higher energetic stationary state to some lower stationary state, and it emits a radiation. It emits a radiation. Now, how we can calculate the energy of that radiation? How we can calculate the frequency of the photon that is emitted by the atom? Here, this is as per the conservation of energy. This postulate is as per the conservation of energy, and he applies here the quantum concepts, early quantum concepts proposed by the Max Planck and the Einstein. The frequency of the photon emitted. The frequency of the photon, because when the atom makes a transition from some initial state, higher energy state to lower, it emits radiation. Now, what is the frequency of the radiation? What is the frequency of the photons that are emitted by the atom? The frequency of the photon emitted in this transition is related to the change in the atom's energy. That is related to the change in the atom's energy. In Rutherford's model, because as per the classical theory, the frequency of the radiation as emitted by the electron when it is revolving, as per the classical theory, it depends upon the frequency of the electron in the orbit. It depends upon the frequency of the charged particle. More will be the frequency, more will be the frequency of the electron in the orbiter, more will be the frequency of the emitted radiation. But here the Bohr says that when an electron makes a transition from one energy state to another energy state, when it makes a transition, the energy emitted, the radiation so emitted, the photon so emitted, the frequency of that photon, that depends upon the change in the atom's energy. And I write in the bracket is that and is not equal to the frequency of the electron's orbital motion, as proposed by the classical theory. Here he has incorporated the quantum concept in his atomic theory, this third postulate, and is given by, we know that from the Max Planck's theory, if a photon has an energy that is equal to h nu, then it is equal to E initial minus E final is equal to h nu. This is the energy of the atom when the electron was in the initial energy, higher energy state. The energy of the atom was this one, and that means in one of the states, initial energy state. Now, when it makes a transition to some final lower energy state, some E final, this is the lower energy state. So, difference between these two energy states, that will be equal to the energy of the photon. This is as per the conservation of the energy. Here we have applied the principle of conservation of energy in the third postulate and quantum concept H nu, Max Planck. Or this is the photon, this energy. So from this expression where here we can write that where E initial is greater than E final. E initial is greater than E final. EI is the E initial is the energy of the initial state and E final is the Y, and E final is the energy of the final state. Now from this equation, this equation gives you the frequency of the photon is emitted when an electron makes a transition from one energy state to another energy state. So these were the postulates of the Bohr's atomic model of hydrogen atom. Now, by using these postulates, we will calculate the energy of the status of the status in which the electrons exist around the nucleus. But we know that when an electron, now we will calculate the energy of these status with the help of these three postulates given by the Bohr, which is known as the Bohr's model of atom. Now, when an electron is revolving, let us suppose this is the nucleus, and electron is revolving around this nucleus. This is a positively charged nucleus as proposed by the Rutherford, and an electron is revolving around this nucleus. This is the electron which is revolving around this nucleus. Now, when the electron is revolving around the nucleus, it will revolve with a certain velocity. So therefore, because of the motion of the electron, it has a kinetic energy. Why it is revolving? As per the classical theory, a particle can revolve only around an object when it has some centripetal force, a force towards the center of the nucleus, towards the center of the circle orbit in which it is revolving. That centripetal force is being provided by the electrostatic force between the nucleus and the electron. And when the since both nucleus and the electron, both are charged particles. Nucleus is positively charged particle and this electron is negatively charged particles. So therefore, the total energy of the electron, one is due to its motion, because it is revolving around the electron with a certain velocity, suppose v, it is revolving around the nucleus with a certain velocity v. Because of this motion, it has a kinetic energy. So therefore, the total energy of the electron, that is sum of kinetic energy which is due because of its motion, plus the potential energy, because the electrostatic interaction between the nucleus and the electron, we know that the electrostatic interaction, the electric field is conservative in nature. Therefore, there is another form of energy which is known as the potential energy, electrostatic potential energy. And between two charged particles, if we have two charged particles, suppose Q1 and another charged particle, suppose some Q2, which are separated by a certain distance, some r. How we can calculate the potential energy? That is calculated by the potential energy is equal to 1 divided by, in a vacuum, is equal to 1 divided by 4 pi epsilon naught into Q1 into Q2 divided by distance between the two particles. Now, if we apply the same thing here, we can calculate the potential energy. Let us suppose the potential energy of the system, nucleus electron system in an atom is suppose, let us suppose that is U. Or we can write it as or 1/2 of m, this is mass of the electron, suppose we will subscript E into V square plus. Now potential energy, this is equal to 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught, charge of the nucleus. Let us suppose the charge of the nucleus, let us suppose the charge of the nucleus is due to protons. Let us suppose the number of protons in the nucleus is Z, which is known as the atomic number of the atom. So then the total positive charge is some Z times E, because E is charge of each proton. But this charge is positive charge, this Q1. Q1 is the charge of nucleus here, and it is plus ZE. The charge is plus into charge of electron, that is minus E. The magnitude of proton, charge of proton and the charge of electron, they are same, which is usually denoted by small e, but their natures are opposite. Proton is positive in nature and electron is negative in nature. This divided by the distance, this distance between the electron and the nucleus. This is the potential energy. Now from this expression 1/2 of me v square plus, we will write down some k instead of 1 by 4 pi epsilon e. This will be minus this minus z e square divided by r. Now when we look at this expression, energy expression, there are terms like velocity and radius. So we need to calculate the velocity of the electron in a particular orbit in which we have assumed that it is moving around the nucleus, because as per the Bohr's model, there are certain definite status, stable status in which the electron exists. They may be which corresponds to n is equal to suppose 1, n is equal to 2, n is equal to 3, n is equal to 4, a large number of these stable states around the nucleus in an atom. Now, in different states, it can have some velocity and distance. The distance of that particular state from the nucleus r. So thus we can say that total energy of an electron, that depends upon what is the velocity, that is the sum of the two energy. One is kinetic energy, another is the potential energy. And finally, we see that we have to calculate the velocity of the electron, we have to calculate the distance of the electron from the nucleus. Distance of the electron, then and only then we can calculate the energy of the electron in a particular state. Thus, now we will calculate these terms, and the velocity of the electron and the distance of the electron from the nucleus in a certain stable state. Now first of all, we will calculate the radii of these stationary Bohr's stationary orbitals. Stationary orbits. Let us suppose the electron of some charge E has a charge E. It is revolving around the nucleus of an atom whose atomic number is Z. Z is atomic number. Atomic number. This is the atomic number of an atom. So it means the charge of the nucleus is Ze plus Ze. Plus Ze. This will be because the nucleus will contain Z protons, Therefore, plus Ze, this will be the charge of nucleus. This is the charge of nucleus. And minus E is the charge of electron which is revolving around the nucleus. Now let us assume that this electron is revolving around the nucleus in a certain state. Let us suppose that state is nth state, which corresponds to n value. Now, as this electron is revolving around the nucleus in a circular orbit, so we know that from the classical theory, when an object is moving in a circle, it has a centripetal force. That centripetal force, if we say, let us suppose, if Vn is the velocity, which is the velocity of electron in nth orbit, and let us suppose Rn, this corresponds to Rn. Suppose the electron is revolving around the nucleus in nth orbit. Let us suppose the distance of this orbit from the nucleus, the radius of this orbit is suppose Rn, and get the distance of electron from the nucleus, it is Rn. This is radius of the orbit. Radius of the nth orbit, in which the electron is revolving around the nucleus. This is the velocity of electron in this same orbit, in the nth orbit. Now, it is moving it follows the circular path. From the classical theory, we know that when a particle is revolving around in a circle, when a particle is following a circular path, it has to, there will be a force which is known as the centripetal force. That centripetal force, that is given by mass of the particle which is moving, that is the electron, mass of electron, into the square of the speed with which it is moving in the circle to the distance of the particle from the center of the circle in which it is revolving. So this is known as the centripetal force. It is directed towards the center of the circle. And since centripetal force is the real force, and the origin of the real force is a matter, is a material. And here the centripetal force is provided by the electrostatic interaction between the electron and the nucleus. Because nucleus will attract it towards itself. Because this is positive in nature, this is negative in nature, it will attract it towards itself. So it is towards this, the centripetal force is provided, this centripetal force, this is the centripetal force, it is being provided by the electrostatic force. And what is that electrostatic force? That is 1 by 4 pi epsilon naught. This is known to us from the Coulomb's law in the first chapter, electrostatics, into Ze into E, this is in magnitude, divided by Rn square. This is the centripetal force is being provided by this electrostatic interaction between the nucleus and the electron. Or we can write it as Me Vn square. Now we'll bring this Rn to this side. This is Rn square is equal to. Now instead of this we will write K. K is actually 1 by 4 pi epsilon. Now we know the value. Value is 9 into 10 raised to power 9 approximately. K into Ze square into R into N. This R into N. I have shifted this Rn square this side and this Rn to this side. Or we will write here m e square Vn square Rn square is equal to k z e square into me into Rn. Here I have multiplied both sides by mass of the electron. Because here was only one me. I write here me square. And I write another me on the right hand side. This one me and this one me. Because I have multiplied this equation on both sides by mass of electron. And I will get, on the left side, I get me square, Vn square, Rn square is equal to k z square me into Rn. Or Rn is equal to, this Rn is equal to me square Vn square Rn square divided by this k m of e z e square. This is equation first. This is equation first. Now, what is this? This is actually the square of the momentum, angular momentum. Or we can write it as me Vn Rn whole square divided by k me z e square. Now here, we will determine that from the classical theory, we will determine that. Now, we will determine the angular momentum by using the classical theory. When a particle, suppose electron, it is revolving around the nucleus at a distance Rn. So with respect to nucleus, the position vector of the particle is Rn. And it is moving in a circle. The direction of the momentum is tangential, that is P, which is equal to m into Ve. So therefore, we know that the angular momentum L can be determined as R cross P. From the classical theory, it is R cross P. And for the electron in the nth orbit, we can write it as it is equal to R of n vector cross P of n vector. Or we can write it as R of n, or magnitude. We will write here magnitude of L is R of n into P of n into sine of angle between R of n. Because this is the radial vector, this is the tangential vector. This is the radius, and the momentum of the electron is along the tangent. We know that in case of a circle, radius and tangent are at 90 degree. So therefore, angle is 90 degree. So we will get it is Rn into m of E, because momentum can be written as mass of the electron into velocity of the electron, and sine of 90 is 1. Or we will write it as m of E into R of n, V of n into R of n. So this is the angular momentum. This is from the classical theory. So thus we can say this is actually the angular momentum. But as per the Bohr's second postulate, this angular momentum, this m V of n R of n, this is equal to, in the nth order, this must be equal to integral multiple of n divided by h pi, integral n into h by 2 pi, where h is Planck's constant. As per the Bohr's second postulate, we have studied this, all the three postulators. As per that postulate, this angular momentum of the electron, which we have calculated classically by using the classical theory, this, as per the Bohr's model, this angular momentum of the electron, this must be equal to integral multiple of h by 2 pi. So therefore, we will substitute. Instead of m of E into V of n into R of n, we will write n h by 2 pi in the equation number second. So therefore, we will write we'll get R of n is equal to, instead of this, we will write n h divided by 2 pi whole square, whole divided by k m of E square into z, or R of n is equal to h square divided by 4 pi square into n square divided by k m of E square into z. or we can write it as h square divided by 4 pi square k m of e into e square n square by z. So this is the radius of electron in nth orbit for a general atom whose atomic number is z. But we are studying here the Bohr's atomic model of hydrogen atom. In case of a hydrogen atom, we know that for hydrogen atom, Z is equal to 1. So therefore, we will write Rn is equal to, this is a constant, the constant, some A naught into n square, where A naught is equal to h square divided by 4 pi square k m e square. When we substitute the values of all these things, h 4 pi k is 1 by 4 pi epsilon naught mass of electron, because these are all constant, we will get 0.53529 angstroms, or we approximate it approximately written as 0.53 angstroms, and is known as the Bohr radius. So that means this Bohr radius is the radius of the first orbit of the hydrogen atom. That is 0.53 angstroms. Thus, from this expression, we will see that the radius of the orbitals around the nucleus in which the electron can revolve, that is proportional to the square of the principal quantum number. That is proportional to the square number. It means that these orbitals are not evenly spaced, rather they are unevenly spaced. Yani the distance between these orbitals goes on increasing as we go away from the nucleus. Thus we can write it as n is proportional to the square of the, that is the radii of the orbitals are in the ratio of 1 is to 2 square is to 3 square is to 4 square is to so on. This is the ratio of the radii of these orbitals. That is 1 is to 4 is to 9 is to 16 and so on. This is the ratio of the orbitals. Thank you.